All right, this work is about describing topological phases and transitions between them using tools which basically originated in quantum information, namely tensor networks. And in particular, I would like to highlight that these tensor networks give us a way to basically holographically describe what's going on in these systems. So they provide a way of describing at the boundary what's going on in a two-dimensional system by translating two-dimensional topological phases into conventional phases in one dimension. Actually, not fully conventional phases, but just one-dimensional phases under symmetries. So I decided not to put any text on the introductory slide, so I will just have some picture which tries to illustrate what the basic idea here is. And the idea in tensor networks is that we want to describe some, say, two-dimensional lattice system, condensed matter system or something like that. And we would like to describe it in some way where we use some local object, some zero-dimensional object, to describe this two-dimensional system. And a very simple way of doing such things would just be to take a product state, right? If you have a product state built from identical states, that's just a zero-dimensional object, that state, and you make a tensor product. But of course, while this works very well in many cases, that's mean field theory, it will of course not capture strong quantum correlations, in particular systems which say have global entanglement, topological entanglement. So we use a more involved method, which I will describe on the next slide. But the main question here is if we try to encode properties of the system in the local tensors, how will they relate to global properties of the wave function? So how do the local properties of this description relate to the global properties of our system? And the point is, what I would like to explain in this talk is that if we want to understand how this zero-dimensional object determines the properties of the two-dimensional object, we basically, it's a good idea to go through a one-dimensional object, which is kind of a slice of this 2D object here, and which basically corresponds to the boundary of this two-dimensional object. So what are these states we're going to use? These tensor network states or projected entangled pair states. So as I said, these form a way to use a local object to describe some extended two-dimensional lattice system. They go under the name of projected entangled pair states, or short Peps, and I will not explain here where the name comes from. And the idea is that what we do is we take some tensor, which is a 5-index tensor, and we will use some graphical calculus. So whenever we have a tensor with a number of indices, like this tensor A with 5 indices, we will just draw a box or sometimes only a dot with 5 legs going out, and each leg corresponds to one tensor index. And if we take two of these tensors and we put them together and connect them by a line, what we mean is that we identify the index sitting on that line and we sum over that index. So we contract that index. So in that case, we identify this index gamma with the first index of the second tensor, and we sum over that index. And if we, oops, this is not supposed to happen, I guess. Okay, and if we sum over that index, so if we do this, we can build a 2D network, right? Just summing over all these indices with Greek letters. And this will basically provide a way of describing some two-dimensional tensor, which is just the expansion of the wave function in the product basis, in the computational basis. And of course, we will have to choose some boundary conditions. And we could choose open boundary conditions. We could wrap the thing on a torus. We could also use an infinite plane, as long as we're not too concerned about the mathematical well-definedness of the limit, or we have a way of establishing its well-definedness. And these states are nice because they provide a very good approximation of low energy states of local Hamiltonians. But they're actually also nice from a different perspective. Namely, we can use them to model physical systems, to model wave functions. And a central reason why we can do that is that if we want to model systems which exhibit a certain symmetry, a certain physical structure, say they're invariant under rotations of all spins by the same angle, under joint spin flips, under reflection, things like that, we can encode that property in this local tensor here. And if we have this property encoded in this local tensor, so you see if you take these local tensors, you put lots of them together, whenever you contract indices, this unitary u will cancel with u dagger, right? So whenever we have a tensor which transforms in this way, whenever we apply a unitary here, we could instead apply unitaries on these auxiliary legs here. Then if we form a 2D grid out of that, these unitaries will cancel out, and we will be left with a wave function which is invariant under that symmetry, if we apply it to all physical legs. So this is also particularly nice because what we can also do in this setup is, so currently we have a tensor which allows us to model a wave function, but in fact the very same tensor allows us to design a Hamiltonian which has exactly that wave function as its ground state. And the main idea is that what we do is we want to take this tensor and we want to build a Hamiltonian which ensures that its ground state can be local. It looks locally like it's being built from these patches, right? So it looks like it's being built from a small patch of that tensor. And now what we can do is we can put Hamiltonians on every 2x2 block, and it ensures that in every 2x2 block, the system looks exactly like it's being built from that tensor. And this means that the global wave function will indeed be a ground state of that interaction, because indeed it looks everywhere like it's being built from that tensor. But the nice thing is that one can actually make statements about the ground space and show that under certain conditions, this is, say, the unique ground space, or it's a controlled ground space of that Hamiltonian. So it's not an uncontrolled construction. So by fixing local constraints, we actually also get global constraints. And the point is that this Hamiltonian we build, because it kind of just makes sure that the state looks locally like it's being built from these tensors, will, of course, enforce that this Hamiltonian is invariant under the same symmetries as a tensor, right? Because we just put together a small number of invariant objects. So we'll just get a new invariant object. So the Hamiltonian just inherits all the symmetries, so we can actually use this to design systems which have certain Hamiltonians with certain symmetries we're interested in, and at the same time allows us to construct the ground state of that Hamiltonian. So the overall picture, the way I like to look at these Peps states is actually as a way to construct solvable models. So usually what people would do in physics is they would start from some Hamiltonian. And of course, you could have a very concrete Hamiltonian coming from experiments, but often you just have some basic structures in that Hamiltonian, right? You want rotational invariance, you want time reversal invariance, particle-hole symmetry. Writing these down, you arrive at something like, say, the Hubbard model, and then you study this model because you believe it captures all the symmetries which should be there in your system and which should govern its physics. And here we can do something very similar. We can start from a tensor into which we put all the properties which we want our system to have. And it will give us on the same footing both a wave function and a Hamiltonian. And we can study how this Hamiltonian and this wave function relate to each other, right? So we basically have a solvable model where we have a Hamiltonian and its associated ground state wave function. And similar to an analysis where we start from a model Hamiltonian, here we want to ask the same question. If we encode a certain property into this tensor, how will it show up in the ground state, in the ground space? Which basically amounts to asking if we have a certain property in the Hamiltonian, how will it show up in the ground space, right? Because the structure of the tensor and the Hamiltonian are basically the same. So the main question I would like to focus on in this talk is, given certain local properties in this tensor, what can we say about the global behavior of this object? Will it reflect the same properties or will it not? And of course, the point is, as long as we would look at finite objects, it will always reflect these properties. But as we make our systems bigger and bigger, it could be that in the limit of a very large system, these properties start breaking down. Okay, so more specifically, what I would like to focus on in this talk is a topological order. So what is topological order? I will be very brief, and I will basically explain it by example in tensor networks, how these things show up. But systems, meaning, well, Hamiltonians or models with topological order, are models which, well, have a range of surprising unconventional properties. For instance, if we look at their ground state manifold, this ground state manifold is degenerate. And it's not degenerate in the way like a conventional, say, Ising ferromagnet is degenerate, because the spins can point up or down. But this degeneracy depends on the topology on which we define our system. So if we put it on a sphere, it might not be degenerate. If we put it on a torus, it will have some degeneracy. If you put it on a higher genus surface, it will have an even different degeneracy. At the same time, these ground states are not distinguishable locally. They all look the same locally, which is also surprising, because in the Ising ferromagnet, we can see if our spins point up or down, and this will make a difference. We will be able to distinguish these locally just by looking at a single spin. This is not possible in that case. So these ground states are really distinguished by global properties rather than local ones. Another property these models have is that when we try to excite them, in the Ising model we can just flip a single spin, that's an excitation. Here the excitations actually turn out to come in pairs. So the elementary excitations of the system come in pairs, and moreover, if we start to move them around each other, they might behave in a very funny way. So although our system is a spin system, the excitations might exhibit statistics which is fermionic or even more exotic when we move them around each other. There are also some more properties, but these are the two main ones which I will explain in the following. But there are more properties linked to these, which are, for instance, the fact that the physics at the edge is robust against perturbations. Or if we look at the ground state wave function and we cut a region and we look at the entropy of the reduced density operator in that region, it will scale linearly with the size of the, with the boundary of the region, but it will have a subleading correction gamma, and this correction gamma is universal, meaning it's robust against perturbations, and it captures topological properties. So it's related, for instance, to the ground state degeneracy. So the simplest and, well, most popular example is Kitaev's toric code. And the idea is basically what we're looking at is that we have a square lattice, and we think of having spins on each edge of the lattice. And whenever the spin is in the one state, the qubit is in the one state, we put a red link, and if it's not, we don't. And what we want is that the ground state of the model consists of all closed loop patterns, of an equal weight of all closed loop superpositions on this lattice. And this is, of course, ensured by local Hamiltonians. And the point is that all local Hamiltonians can do is they can ensure we don't have open loops. And they can ensure that if we have some loop pattern and we kind of grow or shrink the loop, that this has an equal weight superposition. What they can't do is they can't distinguish if we have a global loop around the system. They will not be able to change this local Hamiltonian. What is this? Local Hamiltonians will not be able to change this. And therefore, we have more than one ground state if you say put the system on a torus, right? Because we can have loops going around the torus, which describe a global property, right? Which is not accessible locally. Also, these states cannot be distinguished locally because they're only distinct by some global feature. So how can we model topological order in Peps? And there are different ways to see it. One way to see it is just to start taking, say, the toric code and writing down its Peps representation and analyzing it. I will just postulate and then try to convince you why this is the right way of encoding topological order in Peps. And the point is that what we want is that if we take this tensor describing our model, it is invariant if we act with some symmetry, some discrete symmetry group on all the auxiliary indices at the same time. So the system is in some invariant subspace of the symmetry action. And this is actually very close to what I mentioned before for a physical symmetry, but you will see there's a difference. Before I said that if you act here with some symmetry operation, it translates to such a symmetry operation. Now it's a purely hidden symmetry, right? There's no physical symmetry action. There's only an auxiliary symmetry action. And where the simplest case, which corresponds to the toric code, would just be that this tensor is invariant and I'm putting a sigma z here, or differently speaking, it lives in the even parity subspace. And if you think of each link encoding whether there's a string or not, you can indeed see that the fact that these strings form closed loops indeed corresponds to an even parity constraint. Now you might say that, so before I try to convince you that I want to look at systems with physical symmetries, and I encode these symmetries in my tensor, and then I study what's going on. Now this is not a physical symmetry, right? This has nothing to do with what I see in the Hamiltonian, so you might say this is very much ad hoc. And this is okay if I know what I want to model, but in fact it's not that much ad hoc, because such a symmetry can actually emerge from imposing certain physical symmetries. So say we have a spin 1/2 system, so each unit cell transforms as a spin 1/2 system. We want rotational SU2 symmetry. So we want that if we act with a spin 1/2 representation here, this translates to a spin, to some, well, SU2 representation on these 4 indices. Now what representation could we put there? Well, one option would be to put an integer spin representation. That's not a good idea, because if we take 4 integer representations, we will never get a half integer representation. So maybe we should put half integer representations. But this also doesn't work, right? Because if we take 4 half integer representations, we also get an integer representation. So it doesn't fit. So what can we do? Well, what we can do is we can put a combination of both integer and half integer representations on each link. Because now if you take the tensor product, you will see that you have both integer and half integer representations in there. And you can just pick some of the spin 1/2 ones, right? But this has a consequence, right? Because if you look how you get spin 1/2 or any half integer representation here, you get it by picking an odd number of integer and an odd number of half integer representations. I'm wondering what this relates to. Okay, so it means that because I pick an odd number of the integer ones, or of the half integer ones, I can assign a Z2 symmetry, which counts the number of integer and half integer representations, and I will be in the odd parity sector. It's not exactly the even parity sector, but you can easily see if you take two odd parity sectors together, you do have an even parity sector. So you get exactly such a symmetry emerging naturally from the demand that you want a rotation invariant wave function. So in the end, it's actually not that unnatural to impose such symmetries from physical symmetry considerations. Now, what do these symmetries have to do with topological order? So remember, the condition was that the tensor is invariant if I apply some symmetry action on all these four auxiliary legs. Now I can just multiply it with UG up here, and this is just a rewriting. Well, it seems that some part in the chain declares that there's nothing connected to the video adapter, because it also switches back to the normal screen here. No, the screen is fine. The screen is fine. Otherwise, there should be a fixed time interval, right, between how much I talk and when it happens, and it doesn't seem to be the case. No, it's not plugged in, but I don't think it's that, right? It's not a screensaver, okay? It's not a screensaver. Okay. So what you see is that this I can rewrite this equation in this form. So what does it mean if I imagine putting a string of these symmetry actions, so I just write G instead of UG, along the lattice? It means that I can take this string and deform this string to go through the lattice in a different way, right? And I can continue doing that. So you see what this equation tells me, that whenever I have a string in my lattice, it's basically floating. I can move it through the lattice freely. So it's some kind of pulling through condition, if you wish, right? So strings of this symmetry action can be just pulled through the lattice freely. They're kind of freely floating. And that's really the essence of this condition. It's a pulling through condition. And one can actually generalize it to correlated symmetry action, in which case all known non-chiral topological models, all stringnet models, can be expressed in this language. And this actually gives us a parametrization of the ground state manifold of our system, for instance, because what we can now do is we can put one symmetry string going around the torus in this direction, a second string going around the torus in the other direction, and you see what these strings can be freely moved, right? The claim is that's a new ground state. And why is it a new ground state? Well, if you check what happens if we look at some 2x2 region, remember the Hamiltonian makes sure it looks correct on a 2x2 region, right? So we could look at this region. Clearly, the Hamiltonian will be very happy because it sees the right tensors. So we could have a problem here. But now you see, if you have the Hamiltonian here, we can just use these pulling through equations to take the string and deform it and move it around the region where the Hamiltonian acts. So it's still a ground state, right? There's some extra technical condition that this crossing is movable, but let's not talk about this. So the point is we can put these strings can be moved, which means they're invisible to any Hamiltonian checking locally. We can now use the same kind of strings to build excitations. And the idea is that we also put strings on our lattice, but now the strings have open ends, right? So the strings have endpoints, they end somewhere. And now we see again that what happens is that if we check anywhere along the string, we can deform the string. So there's no energy penalty for the string. It's not visible to the Hamiltonian. But that's not true for the endpoints, right? Because you see the symmetry basically tells us that we can change the number of group actions around the plaquette by 2 modulo 4. But you see this number here is odd, right? So we cannot change this. So a Hamiltonian acting on this plaquette will be able to see that there's something sitting. So the endpoints are actually visible, so they form excitations. And so we have these pairwise excitations, and we can actually see if we try to move one excitation around the other, basically we have to pull one string over the other string. So at least for non-abelian groups, you will see that one group element gets conjugated by the other group element. So you get some non-trivial action in that case. Now, you might think that that's all excitations we can build, but it's not all excitations we can build, and the other excitation is slightly less natural. So the point is the following. What we can do in addition is we can take an irreducible representation action. So for instance, if we have a Z symmetry, we can take a sigma x. And what is the idea? Well, the Z symmetry means that our tensor lives in an even parity subspace, which is, by the way, a stable condition. We can concatenate, and we always stay in the even parity subspace, which relates to things like the topological correction to the entanglement entropy, for instance. And what this X action, say, does is it flips from the even to the odd parity subspace. So it's actually given that symmetry a very natural action to change to a non-trivial symmetry sector. And now if you put one of these guys, you might think they don't come in pairs, right? This is again something which might be visible to a Hamiltonian acting here because we have no rule of moving this. But it doesn't seem to come in pairs. But the truth is it does come in pairs because say we put the whole thing on a torus, we know that the total parity of the boundary must be even, right? Because if we close the boundary, I mean, in the end we only have a point which has even parity. But this changes the parity to odd, right? So we need a second guy somewhere else in order for the total parity to be even of the whole object. So it's kind of a constraint which is also transported by the symmetry, but it's less obvious. But what you also see is if you kind of try to move a loop of these group elements actions around this irreducible representation, you just get a closed loop around them. And if you pull the loop tight, you will pull a group action through an irrep, so the irrep will act on that group element, right? So you will get a non-trivial action again if you braid these things around each other. So it's kind of all contained in the fact that this tensor has a symmetry. It allows you to construct these paired excitations and to determine how they should behave when they braid around each other. And this indeed does, for instance, work out exactly like this for all quantum double models, but it's not restricted to that. Now, the point is, so what I try to convince you is that we can really argue very nicely that if we have this symmetry, that this seems to be very much linked to topological order, and you can indeed check that many known fixed point models say are of this kind. Oh, I forgot to mention one can of course build generalized excitations, which are called dions usually, where you combine one of these guys here with one of these endpoints. Right? So these are usually called magnetic and the other one's electric, but you can combine them to form a joint excitation. In any case, so what I wanted to say, the point is we have seen that there's a relation of symmetry and topological order. It's very suggestive. We have examples. But is it actually is it actually sufficient for topological order? Is it really true that if we have the symmetry, the system is topologically ordered? And the truth is it's not. And one way to see it is, for instance, to take the toric code and then to start to deform the wave function by penalizing states with large loops, right? So we try to suppress large loops by putting what one could call a string tension, right? So we force these strings to get shorter. And of course, you can see if you make this tension large enough, if you suppress long loops just strongly enough, you will be very close to a vacuum state. So this cannot be topologically ordered. There must be a transition somewhere. And the point is that this deformation can be achieved by solely acting on the physical index. Right? You just have to apply a diagonal map which suppresses string states where there's no string states. So this does not affect any symmetry, which only acts on the auxiliary indices. Which actually is a feature, in fact, because it also means that if we go away from fixed point wave functions by deforming things like that, we still have a very nice description of excitations. They don't get fattened like the physical picture. They really stay completely localized. But apparently it also means that these strings we put don't actually describe excitations, right? Because there is a phase transition. We can still put these strings I described earlier, but they don't seem to model anything which is topological. So in some sense that's a blessing and a curse. I think it's more a blessing, but on the one hand it's a bit disappointing, right? There's a symmetry in the local tensor. It doesn't tell you whether you really have topological order or not. Now it's maybe not so surprising, right? If I give you a 2D classical Ising model and I tell you the temperature, it will, you have all the local information, it will not tell you where the phase transition is, right? In the Ising model it will, because you can solve it, but in any even 2D classical StatMech model, you have the local Hamiltonian, which is kind of the same information. You will not know what phase you have. You have to do more analysis. And I think it's very nice because it allows you to encode a variety of different topological phases potentially, as we will see in a moment, just by choosing a fixed symmetry in the tensor. So you can try to explore different topological phases on the same footing without having to assume a priori which one you have. Okay, so what is a mechanism behind this phase transition? So how can we identify, understand, under which conditions these strings I described describe actual anionic topological excitations and when they don't? And what we need to look at are, so as I said, we have 3 different types of excitations. So the pictures changed, but now the tensors are small red dots, right? So what we can do is we had the excitations were strings, right? So we had strings of group actions which we applied between two tensors, which corresponded to an excitation sitting here. We could put irreducible representations on the edge, like sigma x for a Z symmetry. And well, we could combine the two. And let's focus on these two for now. And what are we interested in? If these should describe good, nice topological excitations, well, two things should happen. First of all, if we compare the state with one such excitation, you might wonder why one excitation, but let's imagine we have an infinite plane, right? So we can put the second one to minus infinity. So the string just goes on forever. So we just look at this one excitation. We certainly would like to have that the state with an excitation is orthogonal to the state without an excitation, because it should describe a distinct state. I will put a distinct particle. So I will use this kind of cartoon notation where, say, this creates one excitation with this infinite string. And I look at the overlap with the original ground state. And this should certainly be 0. I want an orthogonal state. If this wouldn't be orthogonal, we would say that this excitation is not an excitation anymore. It has condensed into the ground state. The ground state has a finite fraction of this excitation. So basically I have a new ground state, right, which contains this excitation, so it's not an excitation anymore. The second thing we want is that the single excitation is well defined. So if we look at a state like this or this, and we compute its norm, it should better not be 0, because if it's 0, it doesn't describe a well-defined state. So we want that if you put this in cat and bra, so I will use this kind of cartoon notation, we want this to be non-zero. And under reasonable assumptions, if we separate these guys and the individual expectation value is 0, we expect this decays exponentially, which means these guys are localized excitations, right? So they have some mass if you want. And if this thing would be 0, then we would argue the excitations are confined, because then the only way to get well-defined excitations is to have a pair of excitations close by. So they're confined to be close by. Then we get a well-defined state, but we cannot separate them. So what we want to understand is if these two conditions hold, and when they don't hold, then the system will not be topological or not in the topological phase described by the symmetry we have. And I would like to explain under which conditions this happens, how we can identify this by looking basically at a one-dimensional object. So what object are we interested in? So on the one hand, we're interested in looking at the overlap, right? So we have to take our tensor network and we have to sandwich it with the dagger tensor network. So we get objects like this. And this is, for instance, the overlap of having no string in the lower layer and having a string in the upper layer, right? So this is what I called a dagger earlier. It's the overlap of no string and string. This is what should be 0. We can also compare the overlap of having a string in both layers. And if these guys are very close, or say it's the same side, we want this to be non-zero. We also expect it to go to 0 as we separate them. If it doesn't go to 0, then this guy will also be non-zero. And we might actually also consider pairs of excitations in both cat and bra. This should always be non-zero somehow, because it's not really topological if you put a pair of excitations next to each other, right? And we can do the same for the irreducible representations, which I denote with these yellow squares. We can have a one in one layer, so we have the overlap of state with and without excitation. We have a norm of the state with a single excitation, and then we could look at pairs of excitations. So if we want to compute these objects, what do we have to do? Well, we have to come from one side and contract our tensor network, and we have to come from the other side and contract this network, sum of all indices. So we could cut this into slices, and all these slices are equal except for the region which I depict here, right? We come from minus and plus infinity, and just contract this object, cut into slices. So if we cut it into slices, each slice looks like this, right? So it goes to infinity here and here. We could do it on cylinders if you feel more convenient with it, but it doesn't really matter so much. So what we want to look at is we want to come from left infinity and from right infinity and look at the fixed point of this object. And in between this fixed point, we want to squeeze objects of this form, right? And evaluate them. So what can we say about the fixed point of this guy? And well, now I will say something very hand-wavy. And some of the idea that this object has a locality structure, right? So I would like to think of this object as something like a thermal state of a Hamiltonian at some unit temperature. And we can always do that, right? There's nothing wrong with that because it's just well, there is something wrong with that because it could be non-Hermitian. But let's also disregard that. But I would like to assume that this object has some kind of locality notion, which relates to the locality notion in this operator. And you can certainly write down counterexamples, but they're very artificial. So I would like to argue that if I look at the fixed point of this operator, of course, that's the same as the ground state of this Hamiltonian. So I would like to think of these fixed points as objects which behave similarly to ground states of local Hamiltonians. And I will say, you'll see in a second why I want to relate this. So what could we say about the fixed points of this transfer operator, about these ground states? Well, the main point, the main starting point is that our tensor has symmetries, right? So it's invariant under some symmetry action. And you see if I glue together these tensors to a chain, these symmetry actions will all vanish. And then I put together the ket and the bra layer, and they have independent symmetry actions, right? So what I see that this operator will commute with the symmetry action only in the ket layer. It will also commute to the symmetry action only in the bra layer. And of course, if I would in addition have physical symmetries, I would get more symmetries in this operator. So what it means is that I have some operator, some Hamiltonian basically, with symmetries. And I would like to ask, what can I say about the ground state of a Hamiltonian which has certain symmetries which has this tensor product form? And this is where the notion of symmetry breaking enters, which is kind of the notion to understand different phases in conventional condensed matter systems. And so the basic question is, if I have a Hamiltonian which commutes with some operator, some symmetry, just for simplicity, let me just write Z, what can I say about the ground states of this Hamiltonian? 10 minutes? Okay. Does this include the 2 minutes we spent with a microphone? Okay, so what can we say about the ground states? Well, there are two options. Ground states can be symmetric, right? So in particular, if the ground state is unique, it must have all symmetries. So I will denote it by this kind of all zero state, which is invariant and is a symmetry, right? We could also have the fact that the ground state breaks a symmetry. It doesn't mean that all ground states breaks a symmetry, but if I pick a random ground state, it would not have the symmetry. So for instance, we could have a two-fold degenerate state of all plus states and all minus states, which are swapped by the symmetry. In this context, I could, for instance, also look at semi-infinite strings. So if I would apply a semi-infinite string of my symmetry action, it would still leave this state invariant. Now, this is kind of a cartoon state. If I wouldn't have this cartoon state, which is really fully product, but something close by, these strings wouldn't do exactly that, but they would do something very similar. The claim is they would kind of create a little bit of disturbance around this endpoint, but they wouldn't affect the state on a long distance. On a long distance, it would still be the same state on the left and on the right. I could do a little bit of polishing and all would be looked like before. On the other hand, if I have a symmetry broken state, I apply a semi-infinite string, I will create an infinite domain model, right? I can polish as much as I want around here. It will never look the same as before. And the third thing to note about these states is that there's an order parameter. I can come up with operators X which anti-commute, which are local and anti-commute with the symmetry. And of course, if this guy is invariant under the symmetry, any anti-commuting operator must have expectation value 0. On the other hand, if these guys are not invariant, I should be able to come up with a local operator which has non-zero expectation value, which is called the order parameter of the system. And there are actually even more things, which are so-called symmetry-protected phases. And if there's time at the end, I will get to those. They actually play a very interesting role in this game. So let me just do an example and explain you what happens in that example. And this example will be the toric code system. And so in the toric code, we have the simplest possible symmetry group, which is Z2, right? And so as we said before, we know that our transfer operator commutes with Z2 in the ket layer. It commutes with Z2 in the bra layer. And well, it's a corollary, basically, that then it also commutes with Z and Z in both layers, right? But I would like to look at this separately, because the point is that these guys must behave identically, because there's a natural ket-bra symmetry, right? So I cannot just break the symmetry in the ket layer, but not in the bra layer, because I can just flip them, right? And it must be symmetric. So the independent objects are one of those and this joint object. And well, there are different types of excitations. There's an excitation which has only a string of Z actions. There's one corresponding to the irreducible representations. And it's actually known that these two are the guys which could condense into the ground state. There's a composite object which is a fermion. It cannot condense into the ground state because fermions are not allowed to do that. So let's look at the symmetry and let's ask what are the possible ways in which the symmetry can be broken. And well, it turns out there are 3 ways in which it can be broken. It couldn't be broken at all. It could be that we break the symmetry in a single layer, which means in both single layers, right? Because they have to behave identically. But we break them in an opposite way, so that the joint symmetry is still preserved. Or we could just really break all symmetries. And my claim is now that if I break a single symmetry, but I preserve the joint symmetry, the system is topological, Whereas if I break both symmetries or no symmetry in both cases, it would be a trivial phase. And remember, this is really symmetry breaking in one-dimensional less, right? So I'm looking at the system at the boundary. So in some sense, the claim would be that the amount of topological order results from the difference in symmetry breaking in one layer and in both layers jointly. So how can we see how this happens? So let's take the case I claim was topological, which is a case where the individual symmetry is broken, but the joint symmetry is preserved. And now let's look at the case where we put two strings, one in the ket layer and one in the bra layer. So we have an anion in both layers, and we try to compute the overlap and try to see how it depends on the distance. So if we take our transfer operator and we come from the right, we are in a fixed point of the transfer operator, and we know it breaks a symmetry, so we can denote the state by this broken symmetry, and let's say it's a plus state of the symmetry. Now we put this anion. This anion is just a string of group actions, and if you remember what I said before, such a semi-infinite string of group actions creates a domain wall, right? So we will flip these guys and create this infinite domain wall. Now, if there wouldn't be a second anion, it would just continue. This domain wall would last forever. It would be penalized, and this would not be a well-defined state. But now, which is actually good, right? Because the point is that a single string means we take the overlap of one anion with no anion. They should be orthogonal. But now if we put a string also in the second layer close by, we see that while this acts on the other layer, it will flip the symmetry back, right? Because a joint symmetry is preserved, and both strings together are just a symmetry action of the conserved symmetry, right? They're a z times z symmetry action. So we will undo this domain wall, so all we pay is a price which scales like the separation. So if we bring these guys close together, we see this is a well-defined state. So we really have well-defined excitations which describe these magnetic particles. And we can do the same by looking at what happens to these order parameter type excitations, to these irrep excitations. So if you put them in both layers, we have that we put x in ket and x in bra. It anti-commutes to z-tensor identity, which is good because that's a broken symmetry, so it can serve as an order parameter. It also commutes with z times z, which is also good because z times z is not broken. If it would anti-commute with z times z, it had to be 0, right? Because the symmetry wouldn't be broken. But because it commutes with z times z, it still can serve as an order parameter here. And so it can be non-zero, and it will typically be non-zero if you choose a random operators. So it tells us that this forms a well-defined excitation because its norm is non-zero. On the other hand, if you would just put a single one of these guys, it would anti-commute with z times z, right, suddenly. But z times z is a conserved symmetry, so the expectation value has to be 0, so it means the state is orthogonal to the state with no excitation. So that's a topological case. Now we can look at the non-topological cases, and one case would be where all symmetries are broken. Now if we play the same game again, we put a string here in the ket layer and one in the bra layer. Now there are two order parameters, say one for the ket and one for the bra. We put one string, it will flip one of these guys and create a domain wall. Now we put the second one, it will flip the other layer and create an even bigger domain wall if you wish. Certainly it will not make it go away. So we pay an infinite price because this continues forever, right? It's an infinite domain wall. So this state has norm 0. So it means that this state is not well defined. What we would have to do to have a well-defined state would be to look at a pair of states, because then we would flip each layer 2 times and we would not have a domain wall. So these guys become confined. They can only be written pairwise. On the contrary, putting this order parameter here now means that this order parameter anti-commutes with z times z, which is now broken. So this object alone will be non-zero. So we will have a non-zero overlap of the ground state and the first excited state, and the state with an anion. So this anion actually becomes part of the ground state. And we can do the opposite. In the case where no symmetry is broken, there even a single string of the symmetry will just vanish, right? Because there is no order parameter. So this anion will be part of the ground state. It will overlap with the ground state. And conversely, even putting 2 guys will now anti-commute with z-tensor identity, which is unbroken. So it has to be 0. Okay, so in the last 2 minutes or whatever, 3, let me just, because I think it's actually very exciting, it took us a while to understand this, look at the more interesting case, which is Z4. And while the Z4 has obviously many more ways to break symmetries, because you have Z4 in the ket, Z4 in the bra, you can break Z4 down to Z2, etc. So you get a whole range of symmetries. And there are a bunch of things which you can understand just in terms of what I just explained, which are basically getting toric codes from Z4 in trivial phases. And if you look at a table of anyons, which are labeled by irreps and group elements, it corresponds to condensing either a purely magnetic or a purely electric anyon. But there is this combined particle, which has this half electric and half magnetic charge. And this object is also bosonic. You can condense it. And if you work out the standard rules for condensing anyons, you will see that this is a different topological model, the so-called double Semyon model. Now, if you actually study the model and you look at the symmetries, you will figure out it has exactly the same symmetry breaking pattern in its transfer operator as one of the two possible Toricode models in this phase. So how are they distinct? Right? It's very strange. I just told you that the symmetry breaking pattern tells us which phase we have. And now I'm telling you it doesn't, right? Because there are two guys which have exactly the same symmetry breaking pattern. So this denotes not the broken, but the conserved symmetry. And the point is the following. So what do we need in that case? Imagine we want to condense this anyon into a ground state. It means that if we take the overlap of the empty, the vacuum state, with a state where we have a string like this, corresponding to the, well, group element 2, and an endpoint corresponding to the -1 irrep, that this thing should have non-zero overlap, right? So if you take the left and right fixed point, you have the case that you want that a string with a specific endpoint has a non-zero expectation value. However, you don't want that the string alone has a non-zero expectation value, because then the other object would condense. You also don't want that the endpoint has a non-zero expectation value. So you want that string alone has zero expectation value, endpoint alone has zero expectation value, but the combination has non-zero expectation value. And this is actually exactly what happens if you have symmetry-protected topological order. You have string order parameters. And this is exactly what happens here. This Z2 times Z2 Z4 times Z2 symmetry has a non-trivial phase. And we actually end up in the non-trivial SPT phase of this unbroken symmetry. And this is what distinguishes these two cases, right? The Toricode is in the trivial phase under the symmetry. The double Semyon is a non-trivial SPT phase. So the claim is that to get the full classification, we should look both at the symmetry breaking pattern, but then for the remaining symmetry on the boundary, we should also look at the different possible phases under that symmetry, which are both conventional or disordered phases and symmetry protected topological phases. And well, with this, let me close. And well, I discussed Peps models as a way to model strongly correlated systems, both giving you both wave functions and Hamiltonians. I tried to convey how the topological order in the system is related to a symmetry of the tensor, and that the symmetry leads to a symmetry at the boundary. And if we study the phase diagram of a system under that boundary symmetry, including both conventionally symmetry broken phases and SPT phases, this actually allows us to understand the mechanism under which we get different topological phases from one symmetry. Thanks.
Questions? Yes.
So can you somehow combine the symmetry of the tensor with the symmetry, with the physical symmetry of the system to get like symmetry enriched topological phases or something like this?
Presumably, we haven't looked at that in detail, but I would expect so.
More questions for Norbert? Okay, well maybe the next speaker can come up and let's thank Norbert again.